Welcome! My name is Hiram, and in this video I will show you how the Aspicere framework works in the frontend. JavaScript Aspicere is an implementation of Git repositories and Git hooks for web browsers. The repositories are implemented as Merkle trees, just like Git or Bitcoin. The pipeline is composed by 8 stages: view, create, revalidate, restore, store, post-store, read, and post-read. Developers can hook pico-services in these stages in order to manage things like user interface configuration, permissions management, authorization, data validation, data formatting, compression, encryption, indexing, aspect triggering, among others. Let's see how it works in Chrome. This is a proof-of-concept application programmed with Aspicere and ext-js, but you could use any other framework like Angular, for example. In this app, I can create 4 different kinds of repositories: configurations, authors, gigs, and assignments. Let's create our first repo, an author. An interface or instantaneous interface shows up with the different fields of an author. This instantaneous interface is built on the fly when reading the repository schema. It actually doesn't exist in code. The purpose of interfaces is prototyping and demo. The inspiration comes from the naked objects architectural pattern. You can think of each field in this form as a file. For instance, file alias contains test string. Down here, we have child Merkle trees, or Merklets as I call them. You can think of each Merklet as a folder. For instance, location folders or denomination folder. When I click in location, I'm adding a new subfolder called location with a file GPS course and contents 1,1. When I save the Merklet, it shows up in the list of location Merklets. Currently, in the repository, we only have one client branch, or client version as I call it. When I commit the changes, I can see that the client version is now pointing to the root commit. This root commit has a root Merklet named doc. Doc Merklet has in its turn 6 different child nodes, 5 primitive nodes, and 1 Merklet node. Again, you can think of this as having a folder named doc with 5 files in it and 1 subfolder named locat. The subfolder locat has only 1 file named course with contents 1,1. I can add a couple of denomination subfolders and make a new commit. Each denomination subfolder has 1 file named title. In this case, attempting to add 2 identical denomination subfolders is rejected since there is a pico service checking for duplicates. This is an example of how pico-services can be used to handle logic. Another example is the censorship pico-service, which prevents from adding bad words. A new commit is added to the commit chain. The client version is now pointing to the new commit. The new commit, in its turn, is pointing to the root commit, forming a commit chain or branch if you prefer it. Even further, I can add a snapshot pointing to this commit. A snapshot is equivalent to a tag in Git universe. This is in essence what you have in a Git repository: blobs, trees, commits, branches, and tags. I can add a new version pointing to this commit. And I can continue adding more commits in this commit chain. Versions are useful if the users need to work with many versions of the same document. For example, to make experimental data changes or to create alternatives. As you can see, every piece of information has great traceability. You can see who did what, when, why, and from which system. Of course, this information can be expanded to include even more detailed information. For instance, IP address, web browser version, screen resolution, etc. The security model built in this demo application is similar to the Unix security model. Every file and folder has 3 kinds of permissions: user, group, and other. For instance, the previous commits were done by agent Alice working at Sun. Now, if agent Sue, who works at Sun, tries to make changes to a primitive with owner permissions, the changes will be refused. But if agent Sue tries to make changes to a primitive with group permissions, then the changes will be committed. The same goes for an agent working outside the organization. For instance, agent Bob working at IBM. Then again, the security model is totally customizable. it's possible to use different security levels depending on the needs of the application. As I mentioned previously, the pipeline has 8 stages. The pico-services that hook to those stages are defined in the schema. The schema contains 2 things: data filters, that is to say, the pico-services and nano-services definitions, and data containers, that is to say, the components definitions. For instance, this is the schema for author repositories. In this YAML, we can see the data filters definitions at the top, followed by the components definitions. You can think of a component as a table in a database. A table has columns, which in this case are called primitives. A table has also foreign keys, which are references to other tables. In this case, these references are called component references. Since schemas are prone to become large text files, it's useful to have a graphic visualization. Here we can see the visualization of the data containers as a tree structure with merklets and primitives. And in this diagram, we can see both the data filters definitions and the data containers definitions. Here we can see the different stages in the commit pipeline, and also the subcategories, which are totally customizable. It's worth noting that both data filters and data containers are versioned. In the same way, component references and primitives are versioned as well. This gives the framework great flexibility to adapt faster to business changes in a much organized way. Even the schema itself can be configured. This configuration could be seen as a language to build the schema language, more or less like a meta-language. This allows to customize the level of the nodes, the names, and their attributes, totally painless. The pico-services are small functions which take a merklet and operate it. A pico-service is nothing but a version name coupled with an implementation. Following the Git model, all these repositories and hooks can work offline, so you can build progressive apps without effort. The JavaScript version of Aspicere is built with index database, but the Ruby version is built with SQLite. So repositories can be implemented with both SQL and non-SQL databases. Repositories are totally agnostic to the storage technique. In the future, a specific standard could be developed to manage Aspicere repositories, just like the Git object store. Navigating a repository is also possible even when working offline, since the repository is in the remote side. And this is how Aspicere works in the frontend. A future implementation of Aspicere in Java and Swift would open the possibility to use Aspicere repos and hooks in native applications as well. Some example applications of this technology will be sharing economy apps, case management systems, and any other system where multiple agents, human or artificial, needs to collaborate in the same documents, requiring great traceability, versioning, and offline capabilities. I hope you found less abstract the idea with these concrete examples. Like I mentioned in the previous video, the idea is just to clone the GitHub business model. If you would like to join the development team, or if you are interested in sponsoring this project, do not hesitate and drop a line to my email. Stay tuned for the next video where I show how could support and debugging of Aspicere repos look like using 3D interfaces. See you!